So thank you very much. You see, I'm a little bit handicapped, so I'm not sure if I can stand on during all the time. Perhaps I will sit down, yeah? Yeah? That's much easier for me, yes. Thank you very much. This is a conference on chemistry and environment. That means what can chemistry provide to preserve the environment? And this can be done by chemical reactions, that means transformations of molecules. And chemical transformations occur with a certain rate, and the rate can be affected by catalysis. And that's why the title of my lecture is Elementary Steps in Heterogeneous Catalysis, the basis for environmental chemistry. What can catalysis contribute to the preservation of environment? There are many, many different aspects. The most common application of catalysis is with automotive exhaust catalysts. And we will talk a little bit about the principles of these car exhaust as catalysts. This is associated with preservation of catalysis for clean air, clean water, and clean soil. But another aspect, which I will not address, is catalysis for sustainable energy conversion. This is a very important aspect nowadays, mainly in connection also with electrocatalysis, the formation of electrical current by fuel cells. This I will not address. Then chemicals for the environment. I will show you at the end one aspect where the catalysis is really involved in changing the environment. And then finally the use of renewables. Catalysis is mainly used for removal of toxic substances. And this can be hydrocarbons, the source is chemical petroleum industry, solvents, and car exhausts again. And the main reaction is their oxidation. Then carbon monoxide, the main source of emissions in car exhausts, again is oxidation process. Sulfur dioxide in power plants and heating, it's much more complicated to remove. And finally, nitric oxides, again, the car exhausts in power plants, now it's reduction. So you see there are different toxic pollutants which can be removed either by oxidation or reduction. So it's to find our way where both these processes can take place. This is a total emission of pollutants into the air in Germany in 1989. These are mainly hydrocarbons, carbon monoxide, nitric oxide, sulfur dioxide, and dust. And the red bars is what is caused by the traffic. So the main exhaust of carbon monoxide is through cars, by the traffic. That's why we will discuss this aspect in some more detail. Now, what is catalysis? Catalysis is the affection, the influence of a chemical reaction by the presence of a substance which in itself is not part of the reduction product. And how can such a process can take place? If you look at a chemical reaction, this always involves breaking and formation of new bonds. And if you look at the progress of a chemical reaction, in order to go from a reacting molecule to a product, we have to overcome an energy barrier for breaking bonds. And the height of this energy barrier, the activation energy, determines this rate. And catalysis is now an alternative way for reaching the product by offering an intermediate between the catalyst and the molecules involved in the reaction, by this reaction path is associated with lower barriers, and that's why higher reaction rate. And this minimum here denotes the intermediate formation of a product between the molecules and the catalyst. So catalysis research is mainly associated with identifying and characterizing these intermediates between the catalyst and the reacting molecules. Catalysis is a basis of chemical industry, among others. And if you look what chemical industry is forming, if you look at all processes in chemical industry, about 85% are catalytic. Only 5% are non-catalytic. And among the catalytic processes, the larger part is heterogeneous catalysis. Heterogeneous catalysis means that the intermediate between the catalyst and the reacting molecules is something which is associated with the surface of the catalyst. Catalyst and reacting molecules are in different state of aggregation, gas or liquid and solid, and the reaction is taking place at the surface. This is the main aspect. Only if both partners' reaction and catalyst are in the same phase, this is homogeneous catalysis. And all processes in living organisms are catalyzed by the enzymes. These are macromolecules, large molecules, something in between heterogeneous and homogeneous catalysis. A very small fraction of the industrial processes occurs through biocatalysis. So the main aspect is heterogeneous catalysis. And there's a huge market for the catalysts themselves. And this is shown here over the years. A large fraction is used for petroleum refinery. Another part for automation of chemicals, chemical industry. And then there's the largest fraction, the automotive exhaust catalyst and industrial cleaning processes. And there's a continuous increase of the market. So it's not the use of the catalysts, but the costs of the catalysts is in the order of billions of dollars. Now, what is the principle of heterogeneous catalysis? This is illustrated by this figure here. We have a reactor where the reaction should take place. The reacting molecules flow through the reaction with a certain rate, and the product is leaving the reactor. There's a continuous flow of the reacting molecules. And the catalyst itself, in this case, is a solid, exposing its surface to the molecules arriving at the surface from the gas phase. The atoms in the surface of the solid are missing some of their nearest neighbors, which are present in the interior. So they can form new bonds. It's called chemisorption. New bonds with the molecules arriving from the gas phase. This new bond formation may be associated with bond breaking, dissociation. This is very important. The chemisorped molecules or particles can migrate across the surface, they can find another partner and form a new molecule, which is released back into the gas phase. And the sequence of all these steps determines the overall rate. So it's a question, how can we get information about these individual steps? Now let's go back to the car. The typical composition of the exhaust from an engine powered by gasoline is, of course, nitrogen from the air, CO2, which is another serious problem, of course, water, and about 1% of pollutants. This is the purpose of the car exhaust catalyst, to remove these pollutants, which consist mainly of carbon monoxide, a smaller fraction of nitric oxides, and hydrocarbons. And when regulations were introduced to remove these pollutants from the exhaust by proper catalysts, the result is shown here from the United States. It was introduced in the 70s, and the emission of carbon monoxide milligrams per mile was falling continuously, nitric oxides as well, and the hydrocarbons as well. So nowadays we have regulations which remove to a large fraction these pollutants from the exhaust. And how is this performed? in your car, there's a device. It's a porous support medium of oxide, so-called wash coat, onto which small particles of precious materials like platinum or palladium or rhodium are deposited. And that these surfaces are exposed to the molecules from the gas phase, just for the case of carbon monoxide. And these molecules are interacting with the surfaces. The carbon monoxide molecules are adsorbed through the carbon atom, like in a carbonyl compound. The oxygen molecules may be dissociated, so that we have oxygen atoms chemisorbed and carbon monoxide molecules chemisorbed. They may migrate and meet each other, react and form a CO2, and this CO2 is then released back into the gas phase. Where do we know this from? Now we can look closer to these catalyst particles. And this is a typical supported catalyst particle of platinum on an oxide support. These are very small particles in the nanometer range dimension. And that's why catalysis has been a nanoscience, nanotechnology long before this term was invented. This is because the higher the dispersion, the higher the surface area per gram. And that's why we use catalysts with very small particles. And this is such a particle on a support. And on the surface of these particles, these processes take place. The chemisorption, the dissociative chemisorption, the diffusion, particles meet each other, react, and are released back into the gas phase. We can even look even closer to these particles, and this is shown here. This is again supported ruthenium particles on a magnesium oxide support. And this is a high-resolution electron micrograph of such a catalyst particles with 1 nanometer. These are the individual atoms of the metal particles, exposing the different crystal planes, exposing also crystal defects like steps. And of course, you can assume that all these different sites have different reactivity. This makes heterogeneous catalysis such a complicated process. So in order to get information about the elementary processes, we have to look at the properties of these individual crystal planes. That's the so-called surface science approach. This can be done. This can be done by using single crystals and by looking at the properties of the single crystal surfaces with atomic resolution. This can be, for example, done by the scanning tunneling microscope. And this shows an aluminum 111 surface with atomic resolution, perfect arrangement of the surface atoms, even on a larger scale here. And these are our model systems with which we can study these elementary steps. Aluminum, of course, is not a good catalyst, but we look at platinum next, and we wonder how can such a surface dissociate a molecule like oxygen without great effort of energy. And this can be rationalized with such an energy diagram. Diatomic molecule approaches such a surface, and if the molecule approaches the surface, this is the potential at the end. There will be a weak attractive interaction between the molecule and the surface, and this minimum characterizes the adsorption of the molecule. If instead we dissociate the molecule before, this is dissociation energy, and we approach now the atoms to the surface, the atoms have free valencies, can interact with the surface atoms and make a strong bond with the surface atoms. These are the chemisorbed atoms. Now you see the crossing of these two potential surfaces marks an activation barrier which has to be overcome for a molecule to dissociatively be adsorbed. And this is a secret of the catalyst. This barrier should be not too high, because the higher the barrier, the lower the probability. But the bonding of the atoms should also not be too strong, because they have to react further. And that's why only certain metals or catalysts have the optimum conditions. The car exhaust catalysts, these are just the metals of the platinum group metal. This is a two-dimensional presentation. If you plot the distance of the molecule from the surface, x, and the separation between the two atoms, y. And we have this kind of counterplots. That the molecule approaches the surface, has a shallow minimum, which is the molecular state here. It overcomes the dissociation barrier, and the two atoms separate from each other. We gain energy in this way. This is adsorption energy. This energy has to be released into the solid, and that's why these atoms usually will not stay together, they will fly apart from each other during this time which is needed to dissipate the energy to the solid. So if we look at a surface like platinum, after exposure to oxygen, at low temperatures, we find pairs of new structures. These are the oxygen atoms. And they are separated by 5 to 8 angstroms from each other. They are not in near neighbor sites. Just because of this situation, we need a little bit time, and the time scale is of the order of about 10 to minus 13 a second. That's a typical elementary time for molecular motions on surfaces for separation. And then these are the atoms, and at these low temperatures, they are immobile, they stay there. These bright dots are the position of the oxygen atoms. They are surrounded by dark areas. That's because this technique probes also the electronic properties of the surface. Oxygen is electronegative. It withdraws electronic charge from the substrate, and there's a kind of lowering of the electron density around the oxygen atoms. And as a consequence, the local electronic properties of the substrates are locally disturbed, and this causes some interaction between the particles through the lattice, through bond interactions, like in organic chemistry. They can be attractive as well as repulsive, and we'll show some consequence of this. This is a flat, perfect platinum surface. You see here the platinum surface, where we have the dissociation of the molecules on the flat parts of the surface. As we have seen before, very often, of course, such a surface has defects. The typical defect is a monoatomic step, and these steps can have very strong influences on the reactivity. This is shown here with NO on a ruthenium surface. This is a monoatomic step. And after exposure to a small amount of nitric oxide, 6 minutes after that, we find two new features. These dark points here, these are the nitrogen atoms. And these weak streaks, these are the oxygen atoms. The oxygen atoms are more mobile, and that means they migrate across the surface. The nitrogen atoms are more strongly held, and they need longer time to move away from the steps. So the steps act as active sites in this case. And in detail, it means the following. If an NO molecule strikes such a surface as a terrace, it moves very rapidly to the step. There it can dissociate, and then the atoms move away from the terrace again. The role of these steps, of course, may be that they are the active sites of the catalyst itself. So, and if we have impurities, on the other hand, these active sites may be blocked first. And that's why very often very small amounts of a poison like sulfur kills the activity of your catalyst. This is such a surface with small amount of sulfur. They are just located along these steps, and they are killing the activity. Now we go back to the flat surface with oxygen atoms on it. This is a ruthenium surface with oxygen atoms randomly distributed as a consequence of the dissociative adsorption. And this is a snapshot which was taken in 70 milliseconds, because these atoms are mobile at room temperature. They can move around. And this mobility is illustrated by this figure. If you look at the energetics, if an atom approaches the surface, the potential shows this minimum, which is the strength of adsorption, the adsorption energy, and the lifetime of such a species on the surface is determined by the depth of this potential. If we now move the atom across the surface from one side to the other one, we have to overcome only a barrier for surface diffusion, which is much smaller. And this is why the residence time of such an atom is much shorter. So the molecule or the atom can hop from one side to the other one, depending on the activation energy for diffusion and on the temperature. And with our oxygen on ruthenium surfaces at room temperature, we can now directly follow the motion of the atoms on the surface at room temperature in real time. These are the oxygen atoms hopping around on such a surface at room temperature. On the average, they have a residence time of about 60 milliseconds at one side. Whenever they come close to each other, they stay together a little bit longer because of these attractive interactions I mentioned before. And this has consequences. If we increase the coverage, the concentration, this is a low concentration, they are randomly distributed, they move around like Brownian motion. But if we increase the concentration as a consequence of these interactive attractives, we have a new situation, namely the formation of two phases. A densely packed two-dimensional phase of oxygen atoms and a dilute gas phase. It's like a solid gas equilibrium, which we have here on the surface. So the atoms are continuously attached to the boundary and released back into the gas phase. And this condensed phase is a crystalline phase. We have a well-ordered configuration of the oxygen atoms. And this formation of ordered phases on surfaces is more the rule than the exception, because we have always interactions. And this can be used now to determine the actual structure of these adsorbed particles on the surface by a diffraction technique. Electron diffraction, low energy electron diffraction, is suitable to really determine the structure of these two-dimensional phases. And this is an example of carbon monoxide and oxygen on a rhodium-111 surface. The CO molecules prefer, in this case, these on top sides. This is the side view, and you see these are the distances in angstroms, which are very similar to distances in carbonyl compounds, while the oxygen atoms prefer this three-fold coordinated size, the hollow sides, and form a relatively open mesh. This is the unit cell of the oxygen atoms. Now, if both particles are present in the gas phase, there is a competition for free sites. And the result is the following. As soon as the carbon monoxide concentration exceeds a certain critical value, there's no longer possibility for oxygen adsorption. That's why carbon monoxide blocks the sites. Like in your body, if you have CO there, you cannot take up oxygen anymore, you will die. The same happens with your car exhaust catalyst. If it's blocked by carbon monoxide, oxygen cannot be adsorbed. On the other hand, if we have oxygen atoms, we form this wide mesh, the carbon monoxide molecules can be adsorbed in between. This is a mixed phase between both. This is the rhodium case. Platinum is very similar. We again have this open mesh of oxygen atoms in the hollow sides, CO molecules either in bridge or on top sides, and the mixed phase. Now, if we have a continuous flow of both oxygen and carbon monoxide, the mechanism is the following. The CO molecules have the tendency to form this densely packed layer. The oxygen forms the open meshes. If both particles are present on the surface will be covered by carbon monoxide because oxygen can no longer be adsorbed. Only if the CO concentration is below a certain limit, oxygen can be adsorbed in between the oxygen, between the CO can be between the CO molecules, and we can form the CO2. And this can only be achieved if the temperature is high enough. That's why your car exhaust catalyst is not working at room temperature. You have to go up to about 150 or 200 degrees centigrade, so that part of the CO is always desorbing. And under flow conditions, you have both particles, CO and oxygen on the surface, which may interact and form CO2. This is a sequence of steps. CO is adsorbed, oxygen through a molecular state dissociatively absorbs, and the two recombine to CO2. And this is the energy profile in the sense of showing the action of a catalyst in the beginning. We start with carbon monoxide and oxygen, we end with CO2. This is the reaction enthalpy. Most of this reaction enthalpy is released at the first step by the adsorption of CO and oxygen. And if they are both now in close vicinity, they mean the reaction through overcoming an activation barrier of about 100 kilojoule, which is easily accessible at room temperature or above. CO2 is formed, and then the CO2 is released back in the gas phase. This holds for platinum, rhodium, palladium, but not for ruthenium. Ruthenium is also platinum metal, but it's as metal a very, very bad catalyst. Only if you operate ruthenium catalyst in excess oxygen for a longer period, it becomes active. And this is shown here. The rate of CO2 formation with the ruthenium surface, the rate is expressed in terms of turnover frequency, the number of CO molecules transformed into CO2 per second inside. And as long as the concentration of surface on the surface oxygen is low, there's no activity. Only if you have more than one monolayer of oxygen on the surface, the activity goes up. It becomes even larger. If the oxygen concentration becomes even larger. What is happening here? The oxygen obviously oxidizes the surface. So the catalyst itself is chemically transformed. And this is very often the case, that the catalyst is changing its chemical structure and nature under the operation of the reacting conditions. And in this case, we are transforming the surface of ruthenium with this ordered arrangement of oxygen atoms into a new phase. It's a ruthenium dioxide 110 surface, which is catalytically very active. And its structure is shown here. It exposes ruthenium atoms, these red ruthenium atoms, which are sites which can be occupied by oxygen or by CO molecules. And on these sites, these coordinatively unsaturated sites, the reaction is taking place. Now, theory is now able to even calculate the energetics and the rate of such processes. And this has been done in this case for CO molecules and CO oxygen atoms in close vicinity along these rows of unsaturated sites on the surface. This energy profile for the CO molecule and the oxygen atoms approaching each other along this direction. And there's a barrier of about 0.9 electron volts. That's the activation energy for recombining oxygen and CO molecules and form CO2. This is quantum theory ab initio without any parameters. And one can go one step further and really now measure the rate of CO2 formation under state conditions and compare it with the rate calculated on this basis. And this is shown here on ruthenium dioxide. The rate, of course, depends on the partial pressure of CO, partial pressure of oxygen, and temperature. If we keep the oxygen pressure and the temperature constant, then the rate will be a function of the CO pressure against the turnover frequency. And if we start with a small CO concentration, then of course the rate will continuously increase until we reach a maximum when the steady state concentration of oxygen and CO on the surface are about equal. If we increase the CO pressure even further, the rate will go down again. This is very typical for such a Langmuir-Hinchelwood type of surface reaction. And this is a result of theory. And these are absolute numbers, turnover frequencies, both from experiment and from theory, and there are no adjustable parameters at all. You see, the agreement is not perfect, but it's very good. There's very, very little difference between the maximum and the maximum rate. And this shows that in principle now quantum theory is able to calculate, to predict the behavior of a catalytic surface on simple cases. This is a simple reaction, CO oxidation. Very often, not only a single product is formed, but different products are formed, and the role of the catalyst is not so much the activity, but the selectivity. Selectivity means if from A and B two different reaction products, C and D, can be formed, the selectivity is the ratio of the rate for formation of C over the total rate, and S2 is the formation rate of product D over the total rate. Thus an example is shown here for the oxidation of ammonia on ruthenium dioxide. This is a process which is also applied in industry for the formation of nitric acid, oxidation of ammonia. And again, the rate will be dependent on the pressure of ammonia, of oxygen, and the temperature. If it keeps the ammonia pressure and the temperature constant, and where is the oxygen pressure, we see the rate for formation of nitrogen rises, goes through a maximum, and then decreases again, and the rate of NO formation rises continuously, and this is selectivity. The selectivity for NO formation increases continuously up to about 80%. So it depends on the ratio of the reacting molecules, how high the selectivity is. And this is a consequence of the mechanism of this reaction. The mechanism is shown here. We have this surface exposing these ruthenium atoms onto which either oxygen atoms or ammonia molecules are adsorbed. And if they are neighboring, there is an interaction between the oxygen through a hydrogen bridge to a neighboring hydrogen atom of the ammonia. And this is a very rapid process that takes place at very low temperature. One of the hydrogen atoms is abstracted, and then at higher temperatures, the other hydrogen atoms are abstracted, nitrogen atoms, and water is formed. And then we have now oxygen atoms on the surface and nitrogen atoms, and it depends on the ratio of the two, whether nitrogen atoms recombine to N2 or they recombine with oxygen to NO. So it's the ratio of the oxygen and the ammonia which determines the selectivity of the overall process. And again, this can be modeled by theory. This is experimental results, the full line, and they calculated, and you get a very nice agreement between theory and experiment. This again shows that also very much more complicated reactions can now be modeled. Now, my next example concerns the influence of chemicals on the environment. This is a cut through a tree from a wood in Norway, and you see the rings of the growth every year, the annual rings of the. And at the beginning, these rings were very close. That means the growth was very slow. And after 25 years, these woods were administered with nitrogen fertilizer. So there was fertilizer sprayed through a helicopter over the wood, and you see now the growth increased. There are larger distances. So the fertilizer really has a very strong influence on the growth of these woods. This was an ammonia fertilizer, this was nitrogen fertilizing, and this is an important point for all our agriculture and for the nature, nitrogen fertilization. Until about 1900, there was enough natural source for nitrogen fertilizer, but then the growth of the world population caused really serious problems, and there was a bad need for the formation of nitrogen fertilizers from material which is available in the nature. And this could be achieved by Haber in the laboratory and Bosch with a BAS company, and why it's called Haber-Bosch process. This is a large-scale industrial process nowadays, the formation of ammonia, NH3, from nitrogen from the air and hydrogen. It's taking place in large-scale chemical plants at higher temperatures and higher pressures, with using a very complicated catalyst, a so-called promoted iron catalyst. And the role of this production can be shown here from this diagram here. It shows the growth of the world population over the years and the production of ammonia over the years. And it's very clear that without the formation of ammonia, our world population would starve. Recent estimate says that about 30% of the world population would die because there would be not enough food available. This was a very enormous progress by the formation of ammonia, which is the basis for nitrogen fertilizers. This diagram starts at 2000. Nowadays, about 100 million tons of ammonia are used in fertilizers per year. 100 million tons. Yeah? And about 2% of the total energy consumption arises from this industry. So if it would be possible to find a process which is working with lower energy costs, this would have enormous consequences. But so far, still, this is not possible. The process is based on a catalyst which was invented in 1910 by Mittasch at the BASF, and it's essentially still the same, used in all plants all over the world. This is a catalyst. It looks very complicated. It's a promoted iron catalyst. And this is a scanning electron microscope showing these catalyst particles with this different composition, obviously. The bulk composition is essentially Fe3O4, iron oxide, with small amounts of potassium, aluminum, and calcium. These elements are very important. They are so-called promoters. Without these promoters, the catalyst would not be enough active. What is the role of these small amounts of promoters? Now, these parts here are rising from the aluminum calcium oxide particles, which are embedded between the catalytically active particles of iron. These are the active sites. And these oxides of aluminum and calcium form a framework which prevent the catalyst from sintering at the high temperatures. This is a so-called structural promoter. And the potassium, you see, the surface concentration of the potassium is quite different. The catalytically active spots, these spots here, consisting essentially of iron, are uniformly covered by potassium plus oxygen. This very small concentration of potassium spreads over the surface and forms this promoter. It's a so-called electronic promoter, which enhances the activity for the formation of dissociatively adsorbed nitrogen atoms. This is a decisive step. And this dissociation of nitrogen atoms on the surface depends on the structures. This is, again, are different single crystal surface. The most densely packed one CO plane and the more open plane. The uptake of nitrogen atoms as a function of the exposure to nitrogen molecules. And of course, the activity is highest with this more open plane here. These are the active sites. And this activity can be enhanced by the presence of potassium, because potassium donates electrons to the substrate, and these electrons can be used for back donation into the nitrogen molecule bond, which facilitates the dissociation of the nitrogen molecule and increases the rate of uptake of nitrogen. This is the structure of all of these phases. Nitrogen atoms on the 1 plane. These nitrogen atoms are embedded in the topmost layer of iron atoms, and this is the position of the nitrogen atom. This reacts further. So if one puts together all the information one gets about the individual reaction steps, this is a summary. for the mechanism of this catalytic reaction of ammonia. We start with nitrogen and hydrogen and end up with ammonia. This is the reaction enthalpy. If we would like to perform this reaction into the gas phase by first dissociating nitrogen and hydrogen, we would need an immense amount of energy. Formation of nitrogen and hydrogen atoms. If we would have these atoms, they could recombine stepwise and always gain energy. But this, of course, this is prohibitive. This doesn't take place. Instead, the catalyst offers this alternative route here. The nitrogen molecules are first adsorbed as molecules, and then they can overcome a barrier for dissociation, like the oxygen molecules we have seen before, form the nitrogen atoms on the surface, and the hydrogen atoms are also adsorbed, and now they can recombine stepwise, and the reaction is going uphill. And all these different steps could be identified, and in this way, the overall reaction path can be modeled and is in agreement with the reaction rates formed under industrial conditions. That's the overall mechanism of this reaction, which was a result of a long attempt to identify all these individual reaction steps. So this was my example for chemicals in the environment with a fertilizer. I hoped to have shown to you that heterogeneous catalysis is very important for all these aspects of environmental chemistry. And if you look at heterogeneous catalysis, it is a discipline which involves all the different aspects of chemistry, inorganic and analytical chemistry, in order to characterize the catalysts and to form the catalysts. I didn't talk about organic reactions, but of course a large amount of reactions in organic chemistry are catalyzed. Then we have mainly talked about the application of surface science, physical chemistry, to identify the individual elementary steps to form kinetic laws and understand the bonding, that means the thermodynamics of this reaction. And then industrial chemistry has to put all these things together to understand the solid handling, the chemical reaction energy engineering, and the mass and heat transfer in these catalytic processes. This is a wide field, and there's many, many open questions. I didn't address all the problems concerned with energy conservation and energy transformation, so there's much to do also for the future. Thank you very much for your attention.